morning. I just get a good morning. Very loud one, please.
Good morning.
Loud one. Sorry, part of these lectures will be to get you guys to talk. It's compulsory. It's part of your education system. You're going to be talking all the time as engineers anyway, unless you're thinking of joining academia. Then you'll still be talking. You'll be teaching. So, a loud good morning, please.
Good morning.
Louder.
Good morning.
Thank you. Anyway, that's terrible. We'll work on that one. I'll try to start the Wednesday lectures slightly later than today, basically, because this morning, and I understand getting here in the morning is difficult. I'm recording the lectures. Hopefully, it will work, and I'll put it up on put a link up for you guys on Vision. So today is an introductory lecture. We'll get through some of the material, and it will be fairly slow. And we'll do some questions as well if there's time. If not, we'll do them tomorrow. And I'll be going through my notes here and there. It's my first time teaching this module, so bear with me. Just little background. My name is Dr. Michael Weiss. Please call me Michael, because again, part of your professional development, you're never going to use people's titles in Western Europe, unless you're planning on working in Germany. Then you need to call them Heinz, Herr Doktor. So my background is thermodynamics, slightly more advanced than this, and mainly on the chemical engineering side. So this thermodynamics course is mainly the mechanical side of thermodynamics. So I'll go through some of the learning outcomes, but you'll be doing refrigeration compressions for the design and compressors, things like that. So it will progress as you go through the years. Just a little more background again. I've done my PhD here in the Institute of Petroleum Engineering. My background is oil and gas, so a lot of my examples will be, unfortunately, from the oil and gas industry. And I do some consultancy work outside the university for a couple of companies as well, mainly oil and gas design, a bit of agro-processing. So, to get started, this work. So, what are the learning goals of this module? First thing is to learn the thermodynamic concepts. So it will be a bunch of concepts, derivation, things like that. The boring part. This is not working. You need to learn how to apply these to engineering problems. There is a reason we teach you these things. I know it sometimes doesn't seem like it. And you want to also do well in your exam, I understand that. So my goal is to get you through all these three. The learning outcomes is for you to understand and apply the first law of thermodynamics to closed systems. So I'll explain what closed systems and open systems are. For example, we are a system, we are an open system. Our boundary, our skin, we have vapor diffusion through our skin. In closed systems, you have no interaction with the surroundings. Yeah, there again. Drive and understand the volume work. Understand isochoric, isobaric, isothermal, adiabatic, and polytropic processes, and then you will apply these to compression, Carnot cycle, those kind of things. So you'll get there. They're actually a lot more interesting than the start of this course, I assure you. And apply these to engineering problems. That's something that is quite important for me, because thermodynamics on its own is quite a dry subject. But if you learn how to apply it and how to apply it to different things, you actually start finding it a lot more interesting. I found it quite boring during my undergrads, did a PhD in it, and it seems to be more interesting now. Okay. So I have some side goals for this module, about 5 to 10%. I know some people will find this quite boring, but I want to prepare you for a career in industry. I assume majority of you will be going to the industry rather than the research and academic way. It will be probably one of you in this whole room that will try to go that route, because no one's that crazy. studying and career management advice throughout, I'll give you some things, probably happen. Okay. I have no idea what happened there. There you go. Have me here. And develop your confidence and communication skills. Yes, we'll be picking you randomly to answer questions, and there's a microphone here which I will be handing around. So don't fear. Believe in yourself, and there's no such thing as can't. So I'll try to avoid death by PowerPoint. I did go through quite a few presentation skills stuff before coming here, and you may not notice these things because I'm boring you already. So why do you need to study? Are we just torturing you? What is the point? Well, thermodynamics governs the laws of the universe. Everything that you will see, everything around you is governed by thermodynamics. And you can people are even applying these concepts to modeling behavior, to financial modeling. Actually, quite a few chemical engineers end up in the finance industry because of the mathematical skills, also the conceptual skills. They tend to make a lot more money than most of us. And thermodynamics is the principal building block of engineering. Everything you will do for the rest of your career, if you stay in engineering, will have thermodynamics. So let's say you're designing a distillation column, you'll have to go through the thermodynamic side of it. Yes, a lot of your fellow chemical engineers would have difficulty with these things, and I've seen professionals, 20, 30 years of experience, who don't know the difference between different thermodynamic concepts and which equation state to use and when, and they just go through Aspen and all the simulation software. So after these modules, you'll be better than them, hopefully. So this course is quite a mixed bit of stuff. I'm not quite sure who put it together, I'm just teaching it. It's a slightly different approach that I would have used. The primary goal is to understand compression and expansion. So this applies to compressors, to oil and gas industry, so PVT stuff for reservoirs, to refrigeration, which is one of the main concepts of the future. So everything will require some form of refrigeration. Transporting food around the world, you need cheaper refrigeration. Transporting gas around the world, LNG, cooling data centers, for example, if you want to work for Facebook, cooling their data centers, or Google, very good pay, kind of boring jobs at times, but a lot of thermodynamics. Compressor operation, refrigeration, gas transport. So these are some of the things I've already mentioned. And also, you'll be going through chemical reactions. I'm not sure why that is in there, but it'll be interesting. So, what is thermodynamics? So I'll be going through my notes here because I found some good stuff on this. Thermodynamics was developed in the 1800s, in the time of the Industrial Revolution. So it's been around for quite a while. You're modeling the motion of heat. So think about the production of steel, power burning fossil fuels. The beginning of basically the beginning of all the global warming problems. For the Americans, yes, it actually is a problem. Just messing. It was, for example, global warming, effect of CO2 was modeled by Arrhenius about 200 years ago. And he calculated that we will have problems with global warming based on his thermodynamic modeling in 2,000 years. Unfortunately, we've produced the amount of CO2 he's mentioned to be a problem in a matter of 200 years. So we've already reached and passed his model. So thermodynamics is basically the universe around you. It governs the universe around you. It governs biological systems. For example, your body. You're burning ATP, creating heat. So every single one of you is producing about 200 watts of heat right now in this room. So if you count the number of people in this room, the size of the room, you can calculate how much heat needs to be dissipated from this room using the HVAC system. Again, if you want to do building services at any point in your career. It's part of a mechanical system, cars, boats, planes, everything basically. So it's pretty much the principle of engineering. So we'll be focusing on classical thermodynamics, the macroscopic properties, rather than the more statistical thermodynamics. We're not going into quantum mechanics or anything crazy like that. So going from going from one equilibrium state to another in a state of macroscopic systems. It's empirical in nature, so based on thousands of experiments. It's not theoretical. The theoretical part of thermodynamics goes into statistical thermodynamics, which is going to be the future if you want to go that route. We will get to the concepts, don't worry. It's not going to be all stories. So what is the first law of thermodynamics? These are based on four empirical observations, based on experimentation. So they weren't developed by mathematical modeling. They're all backed by experiments. The reason that's important is it models the real world. So throughout your career, you need to go model the real world. Your simulation tells you one thing, but you need to make sure reality follows the simulation rather than simulation following reality. So the first law defines temperature. It's common sense. So you have, there is no motion at minus 273 degrees Celsius, absolute 0.1516, so 0 Kelvin. Temperature is defined by a molecular motion rather than dissipation of heat. So first law, you can't break even ever. So the concept of energy conservation, you can never break even. You don't lose energy, but you don't gain energy. So you get through the first law. Second law, you can't break even unless you're at 0 Kelvin, right? For example, and the problem, and you can never get to 0 Kelvin, so you can never break even. It tells you if you get to 0 Kelvin, you might break even, and then later it tells you no, you can't get to 0 Kelvin. I'm sorry. So when people talk about producing more energy than putting in, be dubious. So starting with closed systems. What are you doing for time? Okay. What is a closed system? What do you think is a closed system? Anyone? I'm going to pick on you. Randomly. So I've already mentioned we are a system, but we are an open system. How would you define a closed system? I'm sure everyone's seen a closed system. If you think of one, give me an example of a closed system. Guy with Asus laptop, give me an example of a closed system. You know it.
Closed systems that doesn't allow matter in, but allows energy.
Mm-hmm. And what's an example? You know, that's an open system. Good go. Another one? Don't worry. How did you get here this morning?
On bus.
And are there any closed systems on a bus?
Suppose some of the doors.
Piston in the engine? So the piston in an engine can be described as a closed system if because it's burning the fuel and there's no interaction with outside. But this can be anything. So think of a closed piston, like basically what I've put up there. So you have a boundary. As the piston moves up and down, that is your boundary. Remember the word boundary, because I'm going to ask you a question on this later. So this is the moving boundary describes the work that is carried out, right? As the piston moves, you do work. You have a transfer of energy. Why is that important to us? Why am I telling you about a closed system? Where are you going to ever use it? Anyone? So, I mentioned my background is oil and gas, right? Can you describe a closed system that you want to understand in the oil and gas industry? Understand which, if you understand, you can actually use and cultivate energy. Where does oil come from? Where does gas come from? Give me an answer. Someone, please. No? So you get oil and gas from a reservoir, right? It's a closed system. So you have to understand what goes on in it. It's the same, compressors, the same applies. So a lot of the systems around you are not closed, but if you understand closed systems, you can understand open systems. You can understand transfer of energy, heat, work being converted to heat. So you can calculate, for example, if you have a compressor, when you compress air, what's going to happen? You're going to have heat. If you expand the air or expand the gas, you're going to have basically your system is going to cool down. And we'll get to the, for example, things like Joule-Thomson effect in a few lectures time. So oil and gas industry, gas processing. So CO2, natural gas, H2. So you use hydrogen in the food industry all the time. You use nitrogen in the food industry. So I think you've seen these. We finally got to the study guide. I know all of you guys absolutely love this study guide for some reason. Everything I will teach you is from the study guide. There will be things around it, but if you don't like anything on these slides, just go through the study guide. I know a lot of people, there's no new material. Just to emphasize, there's no new material. I don't want to hear complaints, you're teaching new material. Sometimes I'll use the actual material from the study guide. Sometimes I'll use a couple of different books. I think my favorite book is Applied Thermodynamics by Yusuf Çengel. I think it's the third most bought thermodynamics book in the world. I think it's from Michigan State University. So, consider a piston. You have a frictionless, weightless piston. It's not moving. Why is it not moving? So your external forces and your internal forces are exactly the same. So to move this, you need to follow the first law of thermodynamics. If you apply a force, Fp, to your piston, it will need to exceed the current force exerted on that piston. So you have this piston, you apply force, it moves. Right? Simple concept. So the F external on the new system will equate to the pressure, external pressure, times the area, which is the force. F equals PA, right? So at this point, the F external on the first piston equates the force internal. If you exert a new force, it will actually that's not the right one. So if you exert a new force, it will be the summation of the two forces. So F external plus Fp. And so you can actually calculate the new pressure using your forces. So your new pressure equals the external pressure plus the force applied over area. So your new pressure. Yeah? So you have two pressures. What about volume and temperature? What happens then? Well, quite a few years ago, think about over 200 years ago, someone came up with the ideal gas law. Now, this is the first building block of the equations of state. Have you guys heard of equations of state, by the way? Can I get a hands at least if you've heard of equations of state? Okay. And they're usually referred to as EOSs. EOS. So I think in case you've seen EOS in there and don't know what it's talking about equation of state. So this is the first equation of state. There's quite a few afterwards. There's Van der Waals equation of state. I think a lot have seen it in physics. Then you'll have Henk-Robertson, you'll have SRK, things like that. But in this case, we're just looking at ideal systems. So you can calculate the volume and the temperature based on the ideal gas law if you have two of the parameters. So if you have P and V or P and T. Yeah. I think you get the point. First law of thermodynamics. So your total energy equals the heat plus the amount of work that is done by a system. Yeah. So the change in total energy of a system equates the sum of all the energy exchange between the system and the surroundings. I think that's in your notes. So in a closed system, there's no mass transfer. But everything, all the energy transfer, how much energy you will consume depends on the path function. So what path you take. And I'll get through some of the paths you can take. So if you, for example, if you first compress, keeping the heat constant, or if you increase the heat, keeping the volume constant, you will have different amounts of energy consumption. And I'll show you that in graphs in the next slide. So imagine you're expanding 3 moles of hydrogen, which is a gas, at 5 bar and 100 degrees Celsius, to 1 bar and 50 degrees. So if you first decrease its temperature and keep your pressure constant, and then change the pressure and keep your temperature constant, that's one of your path functions. So how do you decrease the pressure? How do you keep pressure constant but decrease the temperature in a system, do you think? Remember PVT. Shall I pick on someone or just give you the answer? I'll give you the answer, I'll be nice. So if you want to decrease, if you want to keep the pressure constant, then you need to compress. So you need to increase, you need to have constant compression to keep the pressure constant, right? So you increase the volume. You decrease the volume. So imagine a piston, and you're decreasing the temperature. Again, the gases are getting farther and farther apart, so the pressure is decreasing. So all you do is you move your piston more and more. You can also take a direct approach. Now that can mean less energy or more energy depending on your calculations. So you can basically decrease the temperature and pressure at the same time, but it needs to be in equilibrium. So you decrease the pressure, you decrease the temperature, and that's more of a real system, by the way. That's how most real systems work. And we'll get to what that means in this course in a bit. A lot of this course, unfortunately, a lot of the start of this course is quite dry, so I'll get through them as quickly as I can. And I'll give you some questions to do today so you understand how they apply. So, thermodynamic properties. What are thermodynamic properties? I think you've studied this before, actually. So they're path independent. They will never change with the path. Whatever path you take, your thermodynamic properties at that specific point will always be the same. So at a specific pressure and temperature, your thermodynamic properties is always the same. Can you name some thermodynamic properties? Or one? Go for it. Yeah, go. Yeah, enthalpy. Yes. Some more commonly used ones. Entropy. Okay, not as commonly used, but it's fine. I'm thinking, let's say it's cold, and you're a skint student, and you have a car, and you have a diesel car. Is it better to put diesel in your car on a cold day or a warm day? When would you get the most value for money? That's a thermodynamic property. So if you go to a petrol station, put diesel in your car on a cold day, because the density of the diesel is higher, or rather the density is lower, you'll get more value for your money. So density is a thermodynamic property at that specific temperature and atmospheric pressure, right? So you also have thermoconductivity, again heat capacity, all these are thermodynamic properties. So in closed systems, again, it's a non-flow system. There's nothing going out, there's nothing coming in, right? I want you to have remember this, and I'll come back to it, and I'm going to put this up every once in a while. The change in internal energy of a system is equal to the heat added to the system minus the work done by the system. Right? This applies to both closed and open systems. And I'll give you I think I'll get you an example of this for isothermal process today. That's a PBT system, PBT setup in a lab. That's actually from my work. So just to put it into perspective, that is a closed system. That's a high pressure piston, right? So you have another high pressure system in that little red box. And if you can see, there's an inlet and an outlet. So you have cooling fluids going around them. That way you can actually simulate an isothermal process. Right, so you can keep the temperature constant. Now, using all this, you can predict the phase behavior of gases, things like that, and that way you can calculate what goes on in a gas reservoir or in a compressor and all that. So you can use these data, and again, focus on the data. You can use the data to model using equation states. You will go through this in third year and fourth year. But just give you an example at the moment. So we will be going through isochloric processes. So what's an do you guys know what's an isochloric process? You show me hands, I won't ask you. Yeah. Okay, some know. So isochloric means your volume is constant. So your temperature and pressure changes, but your volume remains constant. Isobaric process, another hand. Same people. That's constant pressure. So your pressure doesn't change, your temperature changes, and your volume can change. Isothermal, your temperature remains constant. Adiabatic, you have no heat transfer. Polytropic is the real world effect. So your pressure, temperature, volume, all of them can change at any one point. But because of but at any point, because they're not at equilibrium. So the pressure, volume, temperature of the whole system is not constant, and you have to basically work through it until you reach equilibrium. So let's say you change the pressure. Let's say you have that piston in there. You change the volume, so your pressure and temperature will change, right? If you do it very slowly, it reaches equilibrium, right? But if you do it really quickly, then the temperature and the pressure of some parts of that cylinder will be different from some other parts of the cylinder. And it takes a little bit of time for all the molecules to jump around until it reaches equilibrium. And again, I'm teaching you these concepts at the moment so you can understand how to apply them to the material. So a lot of these are, you go through all the equations and all this, so you can solve the equations and solve engineering problems. And I will give you some problems to solve, including your tutorials. If you have looked at them, they're quite applied. So I'm trying to connect these more to the applied questions. So we're coming back to the first law of thermodynamics, right? So the change in energy equals the heat and work. But the total change in energy is the summation of the internal energy, the kinetic energy, and the potential energy. Now, this sometimes you don't have any kinetic energy, sometimes you don't have any potential energy. You seem to always have, and sometimes you don't have any internal energy. So remember, this concept is not just for chemical engineers; it's for physicists, engineers, chemists, everybody. So, what is internal energy? It's basically internal energy. You have your kinetic energy, energy from movement. So I think most of you have seen this in physics at one point, or at least here. And you have your potential energy exerted by gravity. So mass times gravity times height. All right, I'm showing you this again so you remember it. The change in internal energy of a system is equal to the heat added to the system minus the work. Right? Yeah. So, what are the types of work? Well, work is basically the exchange with the system and surroundings. You have quite a few different types of work. You have shaft work, the amount of work exerted by mixing things. So that's you have mixing a lot of different chemical processes, pharmaceuticals, actually maybe pharmaceuticals, food industry, crystallization. I think that's it. You will cover that instead. So you have electrical work. Again, that could be heat, that could be mixing, that could be anything. That's basically exertion of energy. So you can and all energies are, the sum of all energies equal each other. So if you know the electrical energy, the shaft work, for example, using pneumatic, then you can calculate how much energy your system is going to consume. Hence, you can calculate how much money you need basically to run a process. You can do your operating expenditure for a process. You have piston work, which is the focus of all this, and you have stationary systems, which is your internal energy. Your internal energy equals Q plus W again. Molar conventions. Now, these are some of the conventions we'll be using. Q usually refers to mass, energy in little q, or lowercase q refers to, little q refers to mass, and big Q to molar. If heat is entering your system, it's positive. And when heat is leaving your system, energy is dissipated, it's negative. Remember, these are conventions we'll be using, and these are the most standard conventions, but some of the older books and in some parts of the world, different, the exact opposite conventions are used. So just remember, if you nod your head in Japan, it means no, and if you shake it, it means yes. So kind of like that. It's a convention, it's not always the same. So your work done is from your moving boundaries, right? So when you move the boundary, you do work. So when you move your system, the boundary moves. So when when your piston moves, you do work. So imagine just writing and doing work. In real life, these forces are usually unbalanced. But for the sake of this course, we'll be looking at quasi-static processes. So these, we're assuming the system moves so slowly that you're always at equilibrium. So again, I think, as I mentioned, if you move your piston really quickly, the system is not going to be at equilibrium. It's going to be a very unhappy gas at what happens. If you move it very slowly, so you have your piston, you move slowly, stays there, equilibrium is reached. So temperature, volume, temperature is constant. So that's quasi-static. So for this course, we'll be looking at quasi-static processes. Again, volume work is your boundary work, and volume work is also your mechanical work. So just remember boundary work. I'm going to ask a question on this later. I know you guys like equations, so let's solve some. The work done is the force required to move the piston by a distance, dx, or ds in this case. So from point S, from one point S to another point S, S to this one. Yeah. So in terms of your notes, the work done to move against the external force, a distance of z. So your work done is the integral of z2 over z1. The force required to move the system from z2 to z1. Okay. So, sorry, this didn't seem to work as well as I thought. Since your volume is z times area, so it's effectively your height times area of that system, then the change in volume over the change in distance equals area. So any one point. Yeah. And your dz, the change in distance, change in movement, equals the change in volume over area. Yeah. So you can substitute that into the previous equation, and you have the work done is the integral of the force, the internal force of dV over dA. Since force equals pressure times area, then your integral is PV dV. Right? So your pressure in relation to volume dV. Because we can, yeah. Since pressure is related to volume and temperature, you can actually remove that from your integral because they're constants. Right? They're always either directly proportional, PV, or inversely proportional, PT. And again, remember, work done is path dependent. So the boundary, path dependent, these are the important things to remember. Now, what does path dependent mean? So if you look at the green graph, if you go from volume 2 to volume 1, changing the pressure in the path C, your energy consumption is about 5 kilojoules. If you go through straight, do it quite quickly, go straight to volume 1, you'll use up more energy. And if you increase the pressure and basically go the more natural route, then you'll be consuming more energy. It's a question of efficiency. So the distance the piston moves As you move the piston, you change the volume, you change the pressure, right? And you can see it from the other graph. Getting through things quite quickly. Question for you. You have a rigid tank. I'm going to actually get you guys to do this question. You have a rigid tank. Contains air at 500 kilopascals and 150 degrees. You leave it outside. Yes. It's very warm outside. And it cools down to about 65 degrees. And the pressure drops to 400 kilopascals respectively. What is the boundary work done during this process? You want 5 minutes to think through it, calculate things if you want. Yeah? I'll give you the answer. I'll basically work through the answer for this and then give you a break. I know it's fairly boring so far. All right. Are you guys ready for the answer? All excited? I think quite a lot of people are definitely on the right track. So, the most important thing here is the word rigid. It's a rigid tank. So, boundary movement. Think about the concept before thinking about the equation, and then as soon as you put the equation down, and if you understand the concept, it's quite easy. So, what does that mean? If you have no volume change in a rigid tank, then it's effectively P times 0. So anything times 0 equals 0. Because it's a rigid tank, there's no change in volume, dV equals 0. So no boundary work. Do you want another question, or do you want a break first? Yeah. Can I get a hands up for people who want another question? All right. And can I get hands up for the people who want a break? All right. You can have a break. 10 minutes? All right. Come back at 10:20.